Today we are going to discuss about beam design for torsion. A cantilever beam having a uniformly distributed load 4 kilonewtons per meter squared is considered for this. The span or the cantilever length of the beam is 2 meters. Beam dimensions are 600 and 300. Width of the beam is 300. Height of the beam is 600 millimeter. Cover of the reinforcement is 25 millimeter. Say stirrup diameter as 10 millimeter. Now let's start calculating the torsional moment of the beam. Let's see a beam having a span of 5 meter. Let's consider the span of the beam as 5 meter. Then the beam will be, this is the beam span, this is 5 meter, and this load is 4 kilonewtons per meter square. From this we can calculate the torsional moment. Torsion moments is the moment act on this beam due to the eccentric loading on the beam. The torsion moment can be calculated as, now we have the load, we know the load, and this length also we know, that is 2 meter. Then the torsional moment equals 4 into 2 the per meter load, and we have a span about 5. Then the torsional moment is equal 40 kilonewton meter. This moment for both the supports. For one support, the design moment will be 40 divided by 2, that is 20 kilonewton meter. This is for single support. We calculate the total torsional moment. It has to be divided in between two supports. It will be like this. Now we have supports for the span. Then here we have a 20. The other side also we have a 20 kilonewton meter. So the moment will be divided in between two supports. We have a 40 kilonewton meter. Before starting the design, let's calculate some parameter that required for the design. So when you design a beam for the torsion, you have to calculate the minimum and maximum distances of these stirrups. Or the right stirrups will be like this. For a bit enlarged view of strap. That's because we have to consider this center to center distance of this strap. So our beam height and this center to center distance between these two has to be calculated. The minimum distance or the smallest distance and the maximum distance you have to calculate. Smallest distance is considered as x1 and the maximum, the largest distance is considered as y1. So the height of the beam is 600, width of the beam is 300. Now let's calculate the minimum distance x1. x1 is equals, width of the beam is 300 minus cover is 25, bar diameter is 5 into 2 because two sides are there. Then this becomes 230 millimeter. Then you can calculate the y1 also similar manner. 600 minus 25 is cover plus strap diameter into 2, that is 530 millimeter. So the minimum and maximum distances of the stirrup center in between centers now we have calculated. Then we have to calculate the torsional shear stress. Now let's calculate the torsional shear stress, Vt. This equation is given in the code. We can use this equation directly. Vt equals 2 times T is the torsional moment divided by H minimum square into H max minus H minimum divided by 3. From this you can calculate the torsional shear stress. So since we have calculated all the values, we can substitute. Torsion moment is 20 into 10 to the power 6 for unit conversion divided by h minimum is the minimum dimension of the beam or the section, that is 300 squared, into h max is the maximum dimension of the beam, that is 600 minus h minimum is 300 divided by 3. From this we can calculate the torsional shear stress as 1.24 newtons per millimeter square. Right, now we know the torsional shear stress. Since we know the torsional shear stress, we can check whether the requirement of shear links. Right, now for this example we can consider as the concrete grade as a C30 from table 2.3 of BSAS 110 part 2. We can find the VT minimum and VT max. Minimum stress, shear stress for torsion T7 into millimeter square, VT max 4.38 newtons per millimeter square. Based on the concrete grade we can obtain these values. These values are given in the standard, so you don't want to worry about that. Now let's see what are our requirements. Now our VT, because we have shear stress less than VTU. Our VT is, we have already calculated 1.24. This is 4.838. So VT less than VTU, and VT is greater than VT minimum. That means we need shear reinforcement and also our section is okay, and we need to provide the torsional reinforcement for this section. In this example, now when you do torsion design, before torsion design we have to do the design of the beam. We are not going to do this design of this beam, and we are concentrating on torsional design. We have done this design of the beam previously. Accordingly, let's say our shear stress of the beam is as 0.025 newtons per millimeter. So this is from the beam design, which we may not consider in this exercise, and the V less than VC. Right? This is the data for our design. In this example we are going to consider, because we are not going to go with the beam design that we have done separate videos. Our beam can be separated into two segments. One segment is we need the torsional shear links, and the other segment is we don't want to provide the torsional links, that we can go with the nominal shear links. Now the segment 1 VT is less than VT minimum. In this segment nominal shear links is okay, because the torsional shear stress is less than the VT minimum. Minimum shear stress for the torsional links is greater than the torsional stress, so we don't want to provide the torsional shear links. Nominal links can be provided there. Other segment, when VT is greater than VT minimum, then we have to provide the design shear links, and we have to design for torsion. These are the two things we can get from the previous example. Now we have two areas. First area, we don't want to provide the torsional shear links because it's less than the shear stress is less than the minimum torsional shear stress. When it is greater than that, we have to provide the torsional design. Now let's see how to calculate these two segments. Now, as we discussed previously, now our bending moment torsional shear stress diagram will be like this. As explained, in this area we can provide the nominal links. Here we have to provide the torsional links, because here this area, this point VT equals VT minimum. Here it's greater than, this side is greater, so we have to provide the torsional design requirement. And other area the shear stress is less. Now How we can calculate these values? Here the torsional moment will be kilonewton meter 20. Here also 20 kilonewton meter. So how do we can calculate this value? So the code has provided an equation for this. Say the torsional moment here is given by the T equals Vt minimum H minimum square into H max minus H minimum divided by 3, whole thing divided by 2. This equation is given in the code, so you can use this equation directly to calculate the minimum requirement point where we need to provide the shear reinforcement, because beyond that point only we need to provide the shear reinforcement. This is 0.37, this is 300 squared, and H max is our 600, minimum is 300 divided by 3, whole thing we have divided by 2. Then the moment will be 8.33 kilonewton meter. Now we know the moment there. So we also can calculate these positions where we can avoid the. So I have considered one segment. Now we have calculated the moment point at which we don't want to provide the shear links, and here we have 20 kilonewton meter. So since our span is 5 meter, this length will be 2.5 meter. So from this distance where we can avoid the shear reinforcement in one segment, in this segment we can calculate as x equal from the principles 8.33 divided by 20 into 2.5. This is nearly equal 1 meter. So 1 meter area from this, or 1.5 from there, only we need to provide the torsional links. Other than that, we don't want to go for torsional links, right? I think it's clear to you now. Now we can calculate the torsional links requirements. As we discussed in the beam, this one segment. So this area we can provide the nominal shear links. Now let's see what are the requirements. This equation is also given in the standard. This is the nominal shear link requirement of the code. SV equal 0.4 B divided by 0.95 Fy, right? This is also given in the part 1. So you can use that to calculate the shear reinforcement requirement. Say we are providing T10 bars, then the area is V equal, since we have 2 legs, 78, one bar area is 78, then 157 millimeter square. So we can calculate the reinforcement by spacing 157 divided by SV equal 0.4 into B is our 300 divided by 0.95 into 460 is 10. From this SV we can calculate as, actually here it should be greater, so it should be less than 575 millimeter. Say from this we say provide, since it's a very large space, minimum requirement also we have to consider, say T10 at 250 center to center. So we are going for T10 at 250. Now we have to calculate the design links, that is for this area. So this area, the torsional design link for torsion, right, for this area. For that also code have given the equation. You can use that equation directly. This is given in the part 2 of BS 8110. Point x1 y1 into 0.95 F5 squared. simple equation. You can substitute the values. Since we know area, we know SV, we have to calculate T. Now we know what's the T, 20 10 to the power 6 for unit conversion, 0.8 x1, sorry, 0.8 x1 is our 230 into y1 is 530 into 0.95 into y is equal 460. From this we can calculate the SV less than equals 334 millimeter. Let's say we are providing T10 at 200 center to center. Now I think you know method of calculating the value. This is nothing is there. So now you know the method of calculating the torsional shear link requirement. Now let's calculate the longitudinal reinforcement requirement. In addition to the torsional links, you have to provide the longitudinal reinforcement for the sections. Okay, let's see how we can calculate the longitudinal reinforcement requirement. Additional longitudinal can be calculated from the following equation that's also given in the standard. Greater than ASV FYV x1 plus y1 divided by SV F1. H is the reinforcement bar area 157, F5 is 460, we know that, x1 230, we have calculated, y1 530, so we have already calculated. Then SV, the spacing of the bar for the torsional requirement, that is also we have already calculated, 334 into F5, that is 460. From this we can find the AS as 358 millimeter square. So this total area have to be provided in the section. Now in a section we can, for 300 wide beam we can provide the 3 bars. So each bar we can add there, and the middle we can provide 2 bars. So longitudinal we might have a 3 bars and side we might have a 3 bars. So we can divide this into 6 bars. Then we can add the relevant area to the longitudinal reinforcement and provide side bars. 358 divided by 6, not the 6, should be 8 equals 44.7 millimeter square. So nearly it's equal to T10 bars, right? So what we can do here is we can add this area for each bar, and you can decide the diameter accordingly, and you can provide the T10 bars there, right? T10 bars there. So you can, you know the additional area for this bar 447, so 44.7. So we can add that area to this bar, and you can decide it accordingly, diameter accordingly. In addition to that, we have to check the minimum reinforcement spacing. For torsional links, minimum spacing should be less than 300 mm. That you have to keep in mind. Here we have provided the 200, but we have to make sure during the detailing, we have to make sure it should be less than 300, and also you should make sure to provide the reinforcement at corners. So at least at corners you have to provide it. Now, so instead of dividing into this into 8, you might divide into 6. That is, at corners you have to provide it definitely. So you can provide corner bars, and this one like this also you can provide the reinforcement for torsion. When you have beam width, higher beam width, you might go for a middle bar also. That's what we did in this example. Now I think it's clear to you now the method of calculating the torsion reinforcement. In this example, we calculated the torsion reinforcement requirement, that is minimum requirement, and the area where we need to provide the torsion reinforcement also we discussed. and the method of calculating the longitudinal reinforcement for torsion also we calculated. Right, with that we are going to end the today's discussion. Thank you very much for watching our videos.